we will now move on to two-sided limits, or often just referred to as limits. So remember, in the previous section we did left and right-sided limits. Those were also called one-sided limits. If we're talking about a left or a right-sided limit, you specifically have to say left or right. For a two-sided limit, you don't have to say two-sided, you just say limit, and it's understood to be two-sided. So basically the idea with these is for a two-sided limit to exist, both the left and right-sided limits have to be the same. In essence, all we're saying is if we look at a graph at the specified x value, does the graph coming from the left and the right side meet at the same place? Okay, that's really all we're saying here. So let's look at this graph here. So the limit as x approaches -1 from the left. So here's -1 on the x-axis. So remember, just like we did with left and right sided limits, we could put a vertical line there. That's kind of our dividing line, if you will. So coming in from the left side, this graph's doing that, it hits right there at that point. So all you need is the y value for that point. So that y value there is 5. So the limit as x approaches -1 from the left is 5, just like we did in the previous section. Alright, in step 2, they're going to ask for the right-sided limit at the same place. Okay, so now we're on the right side of the graph and we're following it back and following it back and following it back. Eventually we hit that line we've drawn right there at that same point. So the right-sided limit here is also 5. Okay. Alright, so that takes us to step 3. Step 3 is the two-sided limit. So first thing, note the notation difference here. Notice right there, there's no plus or minus sign like you have with left and right-sided limits. So this is just the limit as x approaches -1. Whenever we see that there's no plus or minus indicating left or right, that's understood to be a two-sided limit. And basically all you've got to do is ask yourself, is this the left-sided limit was 5, the right-sided limit was 5, do they equal each other? Well, yes, that's true, they do equal each other, so automatically the two-sided limit is going to be 5. Okay, so anytime the left and the right are exactly the same, the two-sided limit is also the same. If we look back at the graph, all we're really saying is coming in from the left and the right here, both the left and right sides are hitting at that same point. They're meeting together at the same location. Alright, let's take a look at another one here. So different graph. They're asking for the limit as x approaches +1 from the left. So let's look at +1 on the x-axis. That's right there. So let's do a vertical line up and down just to kind of indicate where we're looking at. We want to come in from the left side, so here's the left side. We go in, we hit right there at that point. So that's 1, 2, 3 units below the x-axis. So that's going to mean that limit is -3. Step 2 will be coming in from the right side. Alright, so we're just on the other side of the graph now. We're over here on the right and we're following it back and following it back and following it back, and we hit right here at this point. That's 1, 2, 3 units above the x-axis. So the right-sided limit is going to be +3. Okay. Notice here that I didn't make any mention about whether you have an open circle or a closed circle. Again, that doesn't matter in limits. That's an algebra concept dealing with exactness. Limits deal with getting close to numbers. Okay, step 3 is the two-sided limit as x approaches 1. So again, our left-sided limit was -3. Our right-sided limit was +3. So are they the same? Well, no, they're not. So if they're not the same, then automatically for your two-sided limit, you'll get does not exist. In other words, you don't have a two-sided limit. Okay. And that's really the only two possibilities on two-sided limits. It's either going to be like question 1, where the left and right were equal to each other, so the two-sided was the same, or it's going to be like this question where the left and right were different, so you get doesn't exist. In other words, there is no two-sided limit. On Hawks, you should see a little does not exist button that you can click on. Okay, let's go to the next one here. So if we look at this problem, this graph, notice they've already got a vertical dotted line going through where x is 4. Anytime Hawks gives you a vertical dotted line like that, they're indicating that there's what's called a vertical asymptote. Okay, so basically in algebra that meant it was a vertical line that the graph couldn't cross. Okay, let's look at what they're asking us here. So step 1, limit as x approaches +3 from the left. Well, +3 is, again, right there. So I'm not going to actually draw the line this time because they've already got a dotted line there for us for the vertical asymptote. We want to come in from the left side. So we're coming in from the left, following along the graph. This graph never quite gets to that dotted line, and there's an arrow shooting downward. So if you go down far enough, forever you'd be at -infinity. And then step 2 will be the right-sided limit. Okay, so we're over here on the opposite side, starting on the right, coming back till we hit our vertical line there. So we're hitting right there. The y value of that point is 2. Okay, so the left and right side don't meet each other at the same place. Okay. So automatically the two-sided limit doesn't exist. Okay. Again, why is that? Because the left and the right are different. Anytime they're different, the two-sided doesn't exist. All right, let's do one more graph here, and I wanted to point out a case like this just in case you run into it. So notice in the question they're asking about the x value 1, and again we have a dotted line where x is 1 here, so it's indicating a vertical asymptote. I'm going to try to zoom in a little bit here for you. You'll see a similar graph on certain Hawks questions. Okay, it's really kind of hard to see on this graph, but if we want to do the left-sided limit, we're coming in from the left, and this graph is shooting upward, and you got that upward arrow there. So if you go up forever, you're going to be at infinity. So we would say the left-sided limit here is infinity. Step 2 will be the right-sided limit. Well, coming in from the right side, we have a similar sort of situation. We never quite get to that vertical dotted line because it's an asymptote, and then there's an arrow at the top. So it also shoots upward toward infinity. Okay. So the right-sided limit is also infinity. All right. Remember, for two-sided limits, we said they only exist if the left and right-sided limits are the same. So the left-sided limit was infinity, the right-sided limit was infinity. So the question is, does infinity equal infinity? And the answer to that is actually no. Okay? The reason being, infinity is a concept. It's not an actual value. You can't write down the number for infinity. It's some number we can't get to. It's so big. So who's to say this infinity on the left is the same exact value as this number on the right? You can't. So what we should be saying is infinity does not equal infinity. And remember, if they don't equal each other, that means we say we do not have a two-sided limit. So in other words, it doesn't exist. I apologize if anybody's picking up background noise as they are working on the roof. Okay. After that, we'll get into some problems where they don't give you the graph to look at. These basically work just like left and right-sided limits did in the previous section. So for instance here, if I plug in 4 into this function, I'm going to get 4 minus 4 over negative 5 times 4 squared plus 80. 4 minus 4 is 0. Let's see, 4 squared is 16 times negative 5 is negative 80 plus 80 on the bottom is also going to be 0. So we get the 0 over 0 case. In the previous section, when we got 0 over 0, that told us factor and cancel. So it's going to be the same thing with this. Okay, so let's go ahead and do that here. In this case, x minus 4 is already factored out as it needs to be. And think about this. Since we got 0 on top and bottom, it means there's a common factor on top and bottom. So if the only factor I have on top is x minus 4, then one of the factors on bottom has got to be x minus 4. And you just need to figure out what the other one is. Okay, so that's simple enough to do. X times negative 5x would give you the negative 5x squared. And then negative 4 times negative 20 would give you positive 80. So your x minus 4's cancel out. So your entire numerator's canceled out, so you do still have a 1 up there. Don't forget about that. So now all we've got to do is plug in our number again. 1 over negative 5 times 4 minus 20. That's going to be 1 over negative 20 minus 20, which is negative 40. Alright, number 6, basically the same idea again. If I plug 4 into here, let's see what happens. Negative 3 times 4 squared plus 48 over 4 minus 4. So definitely 4 minus 4 on the bottom is 0. On the top, 4 squared would be 16 times negative 3 would be negative 48 plus 48 is, again, 0 over 0. So that's telling us we need to factor and cancel. Alright, so let's do that. In this case, it's the denominator that's already factored out all the way. But again, if we got 0 over 0, that means one of the factors on top's got to be the same. One of these is x minus 4. You just need to figure out the other one. So x times negative 3x would give you negative 3x squared. And then negative 4 times negative 12 would give you positive 48. So your x minus 4's cancel. Alright, plug in your number, negative 3 times 4 minus 12, that's negative 12 minus 12 is negative 24. Okay. Number 7, again, same thing. If I plug in 1, I'm going to get 1 minus 1 is 0. If I plug in 1 on the bottom, 9 times 1 squared is 9, minus 9 is going to be 0, so I've got to factor and cancel again. Okay, so in this case, if we factor, the top is already done. On the bottom, since you got 0 over 0, one of these has to be the same thing. And just figure out the other one. So x times 9x is 9x squared, and negative 1 times positive 9 would give you negative 9. So your x minus 1's cancel out. You're still going to be left with 1 on the top. All right, then plug in your number again. 1 over 9 times 1 plus 9 is going to be 1 over 18. Alright, at the end of the last section, you did a little bit on piecewise functions. So you're going to see piecewise functions again here in this section. So basically, remember this. We said left-sided limits went with the less than sign. Right-sided limits went with the greater than sign. That's basically all we had to think about. So if we look at this problem, step 1, limit as t approaches 1 from the left. So you need to identify where 1 is in these intervals. So here's t less than 1 and here's t greater than 1. So that's kind of your two options. Is it that first row or the second row? Well, remember, left-sided is the less than sign, so t is less than 1 here on the first row. So that value is 2.5. Okay, and step 2, for the right-sided limit, we want the greater than sign, because right-sided is greater than. So can you read inequalities from the middle out? So we have t greater than 1 here on the second row. So that's going to mean that's 3.8. For step 3, the two-sided limit. What did we say earlier about two-sided limits? If the left and the right-sided limit are different, then the two-sided limit doesn't exist. So basically, since the left was 2.5 and the right was 3.8, those are not the same. So the two-sided limit does not exist, because they're not the same thing. Okay, there's some more questions on here. Step 4, 5, and 6 are all asking about the t-value 9. So you've got a left-sided limit, a right-sided limit, and a two-sided limit. So let's scroll back up here and look where t is 9. Looks a little different for this number, because notice 9 is not on the end of any of these intervals. 9 is literally right in here somewhere. It's somewhere between 5 and 12. So since it's in the middle of that interval, it doesn't matter if we're talking about left or right or two-sided. It's in the middle of that value. So we're going to be looking just at that row, which is always going to be 9. So the left-sided limit's 9, the right-sided limit's 9. Since 9 equals 9, that means the two-sided limit is also going to be 9. One more piecewise function. So you can read through the question there, but basically they've taken this paragraph and written a piecewise function based on that paragraph. They're asking us about left, right, and two-sided limits here in steps 1 through 3. The t value they're asking about is 50. So you've got t less than 50 on the first row, you've got t greater than 50 on the second row. So remember, left-sided limit, you look for the less than sign, that's the first row, so that's going to be plugged into 10t. T is going to be 50, so 10 times 50 is going to be 500. Alright, step 2, the right-sided limit is going to go where the greater than sign is, so t is greater than 50 on the second row, so we need to plug into the second row. Second row is 500 plus 15 times t minus 50. Again, t is 50 here. Okay. Alright, so 50 minus 50 is 0, times 15 is going to be 0. So you've got 500 plus 0, which is 500. Alright, for the two-sided limit, again, compare your left and your right-sided limit. They're both 500. So your two-sided limit is